All right, let's jump into the area of polar curves. And if we're thinking area, we got to be thinking integrals. So I'm going to save a little bit of time on this. And I'm actually not going to do the proof. Save you a little bit. And here is our new formula for finding the area of regions in polar coordinates. Where we're going to say, let R be the region bounded by the graphs. R equals f of theta and R equals g of theta. That'd be if there are two polar curves, or maybe we got an area inside of an area or something. I don't know. Whatever. Let's keep going. I'll explain it later. Between an angle, theta, and another angle. And we're going to say we have 1/2 f of theta squared minus g of theta squared d theta. But that's if we were to have two different curves. So let's say maybe we had, we wanted to find this area, but we also had like a circle that came through. And maybe we just wanted to find the area between 0 and pi. Between the two of them, where maybe we just wanted this area. So we would say that, well, if this is the black one's in F and the purple one's in G, well, then we would say that we have some integral from 0 to pi. And we'd say it's 1/2 the outside function. Oops, I write prime in there. Prime theta squared minus our g of theta, the other one we just get rid of. Remember that? Wouldn't that be like area between curves and stuff like that? Same game. So possibly we'd be talking about two different functions, or they're not functions, two different polar graphs, and we wanted to find the area. So that's why we would have two. But if we're only dealing with one function, we could also look at this and say if it's just one function, it's from alpha to beta of 1/2 f of theta squared d theta. And that's what we're going to do right now. We're going to mess around with the problem where we only have one region. We want to find the area of the four-leaf rose curve. Well, where r is equal to 2 times cosine of 2 theta. Now, I'm just going to kind of sketch it up. We showed it before. Anytime you have this even amount of thetas in there, that means we're going to be symmetric about the x and the y. So it's going to look a little something like this. A rose curve. And I told you, I'm only going to hit you with those cardioids. Cardioids, circles, rose curves. That's it. So we can see it. There we go. We want to find the area of that rose curve. But I'm going to let you in on a little secret. You go from 0 to 2 pi of this. What were we saying? 2 cosines, 2 theta squared d theta. That answer is going to be 0 every single frickin' time. Sines and cosines from 0 to 2 pi. That's the same exact gosh darn thing. So yes, we want to find the area all the way from 0 to 2 pi to find the entire area, but that is always going to result in a 0. So we need to use symmetry. We need to use symmetry about this. I'm thinking the simplest way, is to find the area of just one little piece of it. One little piece. From 0 to pi over 4. So if we only take this region right here, how much more do we need? So that's 1. We'd need 2, 3, 4, 5. You see it now, don't you? 6, 7, and 8, because it's symmetric. That's the nice thing about these polar curves, is there's almost always some symmetry in it to make our life easier. So instead of setting this thing up from 0 to 2 pi, let's say that the area is going to be from 0 to pi over 4, but we just have to multiply it by 8. Sometimes we'll just do half the region when we do cardioids, and they just say times 2. And now we can say 1/2 our function squared. There's our function, 2 cosine of 2 theta d theta. So let's put that 1/2 and that 8 together. 0 to pi over 4, pi over 4. And there's our 4. And then we have, what is that? 4 cosine squareds of 2 theta d theta. Let's take out that 4. We're left with a 16. And now we're going to have to use that reduction formula, or as your book will call it, the half angle formula. So let's just jump aside. You remember this. Cosine squared is equal to 1 plus cosine of 2 theta, all over 2. It's much easier to write it like this. Which means that if you have cosine squared of 2 theta, it means we just have to double up that number. Instead of calling it 2 theta, what's 2 times 2? 4 theta. Now we can replace that out. So we got to know that reduction formula, or as your textbook calls it, the half angle. So 0 to pi over 4, and now we can place it in and go, it's 1/2 plus cosine of 4 theta, all over 2 d theta. Sweet. Let's go. Don't bring that frickin' 16 in, dude. So we're going to take an antiderivative on 1/2 with respect to theta. That's 1/2 theta. And now we're going to need to take a derivative on cosine of 4 theta. But, bro, what's the derivative of, or what's the antiderivative of cosine? Isn't that sine? And are we going to multiply by that 4? Or are we going to divide by that 4? We're going to divide by it. Now, if you need to do a u-sub on it, do a u-sub. You're all good there. Now let's place everything in where they go. So beautiful. We have a 0 right now. See that 0? Sine of 0 is 0. 0 is 0. So all we got to do is plug in that pi over 4. So we get 1/2 our pi over 4 plus sine of 4 times pi over 4. Oh man, this is just cooked up. This is just cooked up. Oh yeah, minus 0. I got you. So we have 16 times pi over 8 plus, well, those go away, just leave you with sine of pi, and sine of pi is 0, so, oh. It's just 2 pi. And there's our solution. That makes sense. I hope it did. That one wasn't as bad as our last problem, was it? That was a 17-minute problem, and I didn't even finish the gosh darn thing. Just told you, yeah, plug in some points to get the last ones. So that's going to be a lot of our game. Until we start putting maybe circles inside of cardioids, or cardioids inside of circles, or vice versa. And that's going to be our next game. So I'll see you in the next game. And that's going to be about as rough. The next game is about as tough as you should expect on an exam, because you will be asked to find the area of one region inside of another. All right. I'll see you in the next